Hello everyone, welcome back to our channel. Today we're delving into the fascinating world of thermodynamics, exploring the concepts of thermal equilibrium and the Zeroth Law. Thermodynamics, the science of heat and temperature, is like a grand cosmic play where heat energy dances from one body to another, seeking balance and harmony. And at the heart of this dance lies thermal equilibrium, a state of peace where no heat flows between bodies in contact because they found a common temperature. Alongside this, we have the Zeroth Law of Thermodynamics, a fundamental principle that laid the foundation for temperature measurements and introduced us to the concept of transitivity in thermodynamics. It's like the rulebook for the heat energy dance we just talked about. Intriguing, isn't it? So grab your metaphorical seatbelts. It's about to get warm in here. Scene script. Let's start with thermal equilibrium. Imagine you're in a house with different rooms, each at varying temperatures. What happens when you open all the doors? Over time, the temperature in all the rooms will balance out, reaching a state of equilibrium. This is the essence of thermal equilibrium, when two or more systems in contact no longer exchange heat because they've reached the same temperature. Picture this: you have a hot mug of cocoa and a cold glass of milk. Initially, they are at different temperatures. But if you pour the cocoa into the milk, what happens? The hot cocoa transfers its heat to the cold milk until they reach a mutual temperature where no more heat is exchanged. They're now in a state of thermal equilibrium, a thermodynamical standstill, if you will. So in simpler terms, thermal equilibrium is all about balance. It's like a spectacular dance where heat is the dancer, moving from one partner to another until everyone is dancing at the same rhythm. It's the universe's way of ensuring that everything is fair and equal, at least in terms of temperature. But what happens when we introduce a third body into this equation? Well, that's where our friend, the Zeroth Law of Thermodynamics, comes in. But we'll get to that a little later. For now, let's stick with our understanding of thermal equilibrium. It's not just a fancy term for scientists to throw around. It's a fundamental concept that governs much of the physical world around us, from the weather patterns we experience to the way our refrigerators keep our food cool. So the next time you enjoy a perfectly chilled drink on a hot day, or notice that your room has finally warmed up after turning on the heater, remember, you're experiencing the magic of thermal equilibrium. It's not just a scientific concept, but a part of our daily lives, constantly at work, balancing the scales of temperature in the world around us. That's thermal equilibrium in action. Now, let's meet the VIP of thermodynamics, the Zeroth Law. This principle might sound complex, but really it's the unsung hero of temperature measurement, laying the groundwork for every thermometer we use today. The Zeroth Law of Thermodynamics is all about thermal equilibrium, a concept we've already introduced. It's a bit like the peacekeeper of the thermodynamic world, ensuring that if two systems are each at peace with a third system, they must be at peace with each other. In other words, if two bodies are separately in thermal equilibrium with a third body, then they are also in thermal equilibrium with each other. Imagine you're at a party and you have two groups of friends. You're the common link between these groups and you're having a great time with both. According to the Zeroth Law, if both groups are in harmony with you, they should be in harmony with each other as well. In thermal terms, if two systems are each in thermal equilibrium with a third system, they should be in thermal equilibrium with each other. This might sound like a simple statement, but its implications are profound. The Zeroth Law forms the basis for the definition of temperature. It allows us to say that if two bodies are at the same temperature as a third body, then they must be at the same temperature as each other. This is how thermometers work. When we measure the temperature of an object with a thermometer, we're actually waiting for the thermometer and the object to reach thermal equilibrium. Then we can say that the temperature of the thermometer is the same as the temperature of the object. So, the Zeroth Law is the reason we can measure temperature and compare temperatures between different objects. It's like a universal translator for heat and cold, making sense of the thermal world around us. Sounds like a cosmic friendship pact, doesn't it? Think about it like this. If you have a cup of hot tea and a bowl of ice cream, and both are separately in thermal equilibrium with a lukewarm bowl of soup, then your tea and ice cream are also in thermal equilibrium with each other. This might sound a bit perplexing, but it's actually a simple concept. The soup, in this case, is acting as a mutual friend, bridging the thermal gap between the steaming tea and the chilly ice cream. even though they might not seem like they have much in common. Through the soup, they reach a state of thermal equilibrium, a state of no heat exchange. Now let's bring this concept closer to home. Imagine a pot of water boiling on your stove. The heat from the stove is transferred to the pot, and then from the pot to the water inside. Over time, the water and the pot reach thermal equilibrium with each other, and they both get hot. This is why you need to use an oven mitt to pick up the pot, even though the stove's flame isn't directly touching it. The same principle applies when you put a bottle of lemonade in the fridge to cool down. Initially, the lemonade is at room temperature and the fridge is much colder. Over time, the fridge cools the lemonade down until they reach thermal equilibrium. The lemonade gets colder, but the fridge doesn't get any warmer, because the heat from the lemonade is dispersed throughout the fridge and then expelled out the back. And there lies the magic of the Zeroth Law of Thermodynamics. It's the reason why your lemonade gets cold in the fridge, why your coffee cools down to room temperature, and why your pot of water heats up on the stove. It's the law that ensures heat goes where it's supposed to go, and that everything reaches a state of thermal harmony. This law is the reason your kitchen works smoothly. It ensures that when you follow a recipe and stick to the cooking times, all your ingredients reach the same temperature, resulting in a perfectly cooked meal. In essence, the Zeroth Law is the culinary conductor orchestrating your kitchen symphony. And there you have it, a glimpse into the captivating world of thermal equilibrium and the Zeroth Law of Thermodynamics. We journeyed from the simple concept of thermal equilibrium, a state of harmony where no heat is exchanged, to the foundational Zeroth Law, a cosmic friendship pact that underpins our understanding of temperature. These principles, though seemingly abstract, are the unsung heroes of our daily life, ensuring our morning coffee cools just right and our recipes cook up to perfection. So next time you sip a lukewarm beverage or bake a cake, remember the invisible laws at play. If this deep dive into the warm and cozy realm of thermodynamics sparked a flame of curiosity in you, don't hesitate to hit the like button. Share the video with fellow knowledge seekers, and subscribe for more intriguing explorations into the world of science. Until next time, stay curious and stay thermodynamically balanced.